And last but not least, Lonike Faes from University of Maastricht, Netherlands.
Yes, thank you. Hi, everyone. Thank you for being here, and thank you for the invitation to present. So today I'd like to talk to you about our ongoing study in which we try to investigate predictive processing in the auditory cortex. And to illustrate this with a little example, I'd like to imagine you the following thing. You walk through Brisbane, it's a new city for you, and you see this bird, and you hear it sing tweet, 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 tweet. At some point, your brain will learn that tweet, tweet, tweet will be followed by another tweet. So the brain learns to anticipate incoming sensory information. Yet suddenly you hear this bird sing tweet, tweet, toot. Your brain can also signal this deviation from expectation by sending a signal that this toot is different than the tweet that you expected to hear. And how this is implemented in the brain is formalized in a framework that is called predictive coding. That postulates that we have an internal model of the world around us that we learn based on previous experiences. And within this framework, we have different specialized roles assigned to different cortical layers, in which feed-forward and feedback stream perform different roles. In essence, what is thought is that if we have this internal model, it can actively generate predictions that are sent to lower order areas that reside mainly in the deep layers. And these predictions are compared to the sensory input that we actually get into our senses. And this is called a prediction error, which is sent forward to higher order areas. And so we think that errors mainly reside in superficial layers. Now, if we want to image cortical layers or cortical depths in humans non-invasively, we can make use of high-resolution functional magnetic resonance imaging, which is what we did in this study. So what did we do to probe error violations in our design? So we presented sequences of syllables that always contain 3 identical syllables, ba, 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 that could be followed either by a 4th syllable that was the same. This is our standard sequence, a deviant syllable, or we could omit the 4th syllable. And we presented this in a slow event-related design. And so what we hoped was that participants really expected, after hearing 3 bas, that they would hear another ba. Now, the type of data that we collected is sub-millimeter resolution data, so 0.8 millimeter isotropic, and we collected this with gradient echo bold data, which is, for high-resolution fMRI, a nice way of collecting a lot of coverage of the brain. But what is also a little bit problematic in this type of data is that it is biased towards the unwanted macrovascular contribution of the vascular architecture. And so there are a few ways to try and mitigate this problem, and we have used a generative laminar bolt model. This looks a bit daunting, and I won't go a lot into the details, but if you are interested, come and talk to me after this talk or check out our preprint online for the details about this model. In essence, what it does is it's incorporated within the dynamic causal modeling framework, and it allows us to estimate the underlying neuronal parameters that give rise to our measured bolt response. And for the people that know a little bit about this, what we focus on is the modulation of the self-excitation of this excitatory neuronal population. What it means if we look at our results is that a positive modulation corresponds to a higher response to our deviant sequence compared to our standard sequence, and the other way around. So a negative modulation corresponds to a higher response to the standard stimuli. Now, if we look at these results and we map this on top of this standard predictive coding architecture in which we assign superficial layer responses to indicate error responses, we can see here that we, in the posterior SDG, which is an area that responds to speech sound, find error signaling in these superficial layers. In addition, we also find a very widespread deep layer effect that I told you was related to feedback information, and we think that this represents the updating of the internal model of the brain. So after an error is signaled, the brain needs to be informed, and so the model is updated. This is in line with animal electrophysiology that has shown similar results. And what is interesting, and that I briefly want to mention, is in this preprint that I mentioned before, we have used a very similar experimental paradigm, but we used cascading tone sequences instead of syllabic sequences but similar, this predictable condition is similar to our standard, and the mispredicted similar to our deviant condition. And then if we analyze in a very similar way our data, and these are the results, then we find also similar effects. So a superficial layer effect in the planum polare, and also again this very widespread deep layer effect. So it could be that the type of stimuli that we used, tone sequences in this study, syllabic sequences in the other, would move error signaling from a lower order auditory area to a higher order area. And this we hope to test in future studies. But I also mentioned that we had the presentation of omitted stimuli. Now this called for a different type of analysis pipeline. So we did not use the model. And the question is why? So in our design, omission responses were always unexpected. So people always heard these first 3 syllables, and then they never really expected to hear the omission. So when we use the model, we need a very good control condition, which means that in our case, we never measure the bold response to just 3 stimuli. We always measure it with the unexpected omission, which is a bit of a confounding factor. So we decided to use a different processing pipeline in which we try to disentangle the response to the first 3 stimuli from the unexpected omission neural response, for which we needed to determine the hemodynamic response function. So we collected data from a patient population that have undergone the exact same experimental paradigm using electrocorticography. To illustrate that there actually is a response of the brain to omitted syllables, I've put above here the ECOG response. And if you look at the omission response, you can very nicely see that there are responses to the first 3 individual syllables. And there is also a response to the fact that we omit a syllable. So the brain responds saying, like, something is missing. What we did is we then tried to use our ECOG response to the standard stimuli and our measured bold response to try and find the optimal hemodynamic response function to our stimuli. Mind you, we never measured the actual response to only 3 stimuli. So we tried to understand, okay, what is the best hemodynamic response function to try and understand how these 2 are related. And then what we did is we took the ECOG response to the standards, to the deviants, and to the first 3 presented syllables of the omission sequence, convolved this with our optimal HRF, so not with the canonical HRF, but the one we estimated, and we subtracted this from our original fMRI time series. Then what we have left is an fMRI time series that contains some sources of noise and this potential effect to the omitted syllable. And then what we did is we tried to estimate beta values in % signal change in the time window at which we expected to find an omission response. And then if we look at this data, and this is a relatively new thing to investigate using high-resolution fMRI, we find a very widespread effect across all our auditory areas. This is in line with previous animal electrophysiology that has shown omission-sensitive neurons in all layers. But mind you that this is at the moment not a comparison between conditions, and we did not remove the effect of vascular draining. So I think it's a very nice result, and we will look into this a bit further. So in short, we've used syllabic sequences to probe violations of expectations using high-resolution fMRI. For the deviant syllables, we find a error signaling in the posterior STG and a deep layer effect that we relate to global model updating. And the nice thing, I think, is that we also replicate a previous study that we have done. And in addition, we find widespread activation to our omission syllables. And I think we have some ideas of how to try and disentangle these error and global model updating signals in the future. But for now, I'd like to thank you all for your attention. And while I'm at it, because my poster is no longer there, but I have 2 colleagues that are still presenting today and tomorrow. So if you want to see more of these things, check them out today. Thank you for your attention.
Question. We are right on time, so we have
time for a couple of questions, don't we? For the repeated, syllable stimulus, how can you be sure that, how can you distinguish like response to error versus response to just contrast?
When you mean contrast,
Like
you mean?
if you have the same syllable and then a different syllable, it could be just that it's responding to difference between the syllables as opposed to the syllable being unexpected. Like in the other experiment, you had a sequence of tones,
Yes.
so they were contrasted. They were, even when it was expected, they were different from each other, whereas in the syllables, it's the same syllable
Yeah.
and then either the same or different. So
So you mean to say that if we find a response to deviance, it's because they heard a d instead of a b?
yeah, just the response, unless you can be sure one way or the other, it might be a response to just hearing a different sound as opposed to an unexpected sound.
Yeah, so I would say in our stimulation paradigm, there would not really be a way to really disentangle this, but there is a different kind of experimental paradigm that we could use in which this you could actually disentangle. But I would say, does that answer your question?
Okay, yeah. Though it seems like the tone sequence from the other experiment already kind of does avoid this issue.
Yes, that is definitely true, but the primary auditory areas are a bit more difficult to measure using ECOG, like if you place a grid on the surface. So this experimental paradigm was changed in a way so that we would actually be able to measure this with a grid in patients. So you're right, the other experimental paradigm addresses that better, but had another caveat.
All right.
Thanks.
Yes, we have time. Last question.
Can you briefly speculate on the widespread omission results?
Yes, so I think there are different potential explanations. The first one is, as we said, we try to estimate the hemodynamic response. So we don't know the hemodynamic response to just 3 syllables. It's a very consistent finding. Another potential reason could be in the first part of the analysis, right? We use this model, so we remove the effect of vascular draining. And we actually see that if we do not remove this effect, we also have a more widespread effect, because like the biggest influence this model has is at the middle and the superficial layers. And for this omission, we did not use this model. So it could also be related to this difference in the processing pipeline. But also, so in these type of omission responses have not very often been used in laminar fMRI, at least for sure not in the auditory cortex. So this also could explain why, for instance, in visual research, deep layers have been indicated to respond to omissions, and we find a very widespread effect. But if you're interested in this, then Mehdi Einan is presenting a poster that also uses omissions. So,
Thank you.
thanks.
Well, let's thank again all our speakers.